Hey there, science enthusiasts! Today let's dive into one of the coolest remnants of the Big Bang, the cosmic microwave background, or CMB for short. Think of it as the universe's baby picture, snapped when it was just 380,000 years old. So, how did we get this cosmic snapshot? It all started with the Big Bang. This colossal event marked the birth of our universe, initially a hot, dense soup of particles. In the very first few minutes, nucleosynthesis cooked up the first light elements, hydrogen, helium, and a sprinkle of lithium. Fast forward to 380,000 years later, and we hit the Recombination Era. The universe had cooled enough for protons and electrons to hook up and form neutral hydrogen atoms. Before this hookup, the universe was an opaque mess of photons bumping into free electrons, a state known as the photon-baryon plasma. But once recombination happened, the universe became transparent. Photons could finally travel freely without getting scattered. These photons are what we now observe as the cosmic microwave background. They've been journeying across the universe for over 13 billion years, stretching into the microwave part of the spectrum due to the universe's expansion. Now let's talk about the CMB's characteristics. It has a pretty uniform temperature of around 2.725 Kelvin. Yet, tiny fluctuations in temperature, just a few microkelvin, reveal density variations in the early universe. This is what we call isotropy and anisotropy. The CMB is incredibly isotropic, uniform in all directions, but those slight anisotropies are pure gold for cosmologists. They offer clues about the early universe's structure, which later evolved into galaxies and large-scale cosmic structures. And here's a fun fact. The CMB has a near-perfect blackbody spectrum. This thermal radiation from a hot, dense state is one of the strongest pieces of evidence supporting the Big Bang theory. So, why is the CMB so important? For starters, it gives us a direct link to the early universe. By studying the CMB, scientists can probe conditions just after the Big Bang. The tiny fluctuations in the CMB point to primordial density variations that seeded the formation of galaxies and clusters. Detailed measurements of the CMB help us pin down key cosmological parameters like the age of the universe, its composition, and the rate of expansion, the Hubble constant. The data supports the lambda cold dark matter model, which includes dark energy and dark matter as vital components. The CMB also provides insights into the universe's geometry. It tells us that the universe is flat, or Euclidean, with impressive precision. Plus, it helps test theories about the universe's large-scale structure and topology. Major observations like COBE, WMAP, and the Planck satellite have been game-changers in our understanding of the CMB. They've given us detailed maps and high-resolution measurements that refine our grasp of the cosmos. But it's not all smooth sailing. Anomalies like the cold spot and hemispherical asymmetry in the CMB data keep scientists on their toes. These deviations from the expected isotropy are intriguing puzzles we're still trying to solve. Future missions and observatories are set to dive even deeper into the CMB, aiming for more precise measurements and new discoveries. By continuing to explore the CMB, we hope to unlock more secrets of our cosmic past and the fundamental laws of the universe. Thanks for joining me on this cosmic journey. Stay curious and keep exploring